Today we will see the rotational partition function. First we will derive this rotational partition function. First we will consider for an unsymmetrical linear rotator. Suppose AB. This just represents that it is made up of two different elements. Okay, but it is a linear rotator. The rotational energy is given by this expression. That means E rotational is equal to h square divided by 8 pi square I j into j plus 1. So here h is Planck's constant, I is moment of inertia, j is rotational quantum number, and this can be written in this form also: h c p j into j plus 1. So this will be our equation first. And the degeneracy of rotational level is 2j plus 1. So this is the degeneracy. Here B is called rotational constant. And this rotational constant is basically equal to here h upon 8 pi square I c. So this is the value of this rotational constant. And j we know is simply rotational quantum number. And it has values from 0, 1, 2 and so on. So we can write the rotational partition function. That means write this QR as rotational partition function. It will be equal to the summation of, it will run from j, and degeneracy, in place of degeneracy we will simply put the value 2j plus 1, because we already know this degeneracy is equal to, for this case, 2j plus 1, and into e raised power minus beta, which is having the value of 1 upon kt, and it will be the this energy of that means the rotational energy. Okay, now we can use the value of equation 1 here also, so we can write it as summation j degeneracy, that is 2j plus 1 into e raised power minus beta, and in place of this rotational energy we can simply insert the value of h c b j into j plus 1. So this will be our equation second. Since many rotational states are occupied at room temperature, the spacing between successive rotational levels rotational levels is very small. So we can replace this summation with integration. The summation in equation second can be approximated by integration. That is, we can write the equation second as, in place of summation we will simply write it as integral from suppose 0 to infinity. We will give the limit here, degeneracy, and e to the power beta h c b j into j plus 1, and with respect to dj. This is equation. So basically we have to evaluate this integral. So this integral can be evaluated in the following manner. Suppose we will write first t upon with respect to the rotational quantum number into e raised power minus, first we will solve this exponential part here, h c b j into j plus 1. So this can be simplified. Here we will simply multiply the j to this one and this one. So we can write this as t upon dj e raised power minus beta scb j square plus g. and this can be written in this form. If we want to first take the differential of this with respect to this one, it can be written in this form. It is differential of e raised power minus ax type of function here. So we can write it as minus beta hcb equals to, that is the minus e raised power minus ax again, that means minus beta hcb j square plus j into differential of this function, that means d upon dj differential of j square plus j. So this is very easy now to solve. So it can be written as beta hcb, and we can write it this as such. It is for minus beta hcb j into j plus 1 or j square plus j. So this is one and the same. Now we have to differentiate first this function j square. It will be equal to 2j because it is x raised power n, so it will be nx, and similarly it will be dj upon dj, which will be equal to 1, so it will be here 1. That means we have solved this part here. This is basically equal to this part, that means d upon dj into e raised power minus beta hcb j into j plus 1. Here what we do, we will simply take this part here to this side. So we can write here minus 1 upon beta hcb into d upon dj into e raised power minus beta hcb j into j plus 1. So this will be simply equal to the remaining part, which is simply 2j plus 1 into each exponential to the power hcb j into j plus 1. So this is equation. Now what we will do, we will simply substituting equation 4 into equation 3. We get this relation. Rotational partition function will be equal to, this is constant, minus 1 upon beta hcb, so this can be taken out of the integral. So we can write beta hcb, then integral from 0 to infinity d upon dj into e raised power minus beta hcb j into j plus 1 and dj. So this is simply equal to minus 1 upon beta hcb into e raised power minus beta hcb j into j plus 1. We have the lower limit 0, upper limit infinity. So this can be written as minus 1 upon beta scp. This is first, if you introduce in place of j first to infinity, then it will be 0. This part will be then equal to minus 1. So it will be equal to minus minus will be plus. So it will be 1 upon beta scp. Or you can put the values of beta and this rotational constant b back into this equation. So we can write this as kbt, because beta is equal to 1 upon kbt, so it will be kbt, and this is equal to h upon 8 pi square ic, so it will be multiplied by 8 pi square ic upon hc and h. So this will be simply equal to this. For linear rotator, the rotational partition function will be simply given by this expression 8 pi square I kbt, which is simply Boltzmann's constant, temperature upon Planck's constant square. So this is very important relation here. This is for a linear rotator, rotational partition function for a linear rotator. This has basically has dimensions of temperature, and is called this is called a characteristic rotational temperature. Characteristic rotational temperature. And it is also given by this expression. Rotational is simply equal to T upon this rotational partition function. And one more point you have to remember is that at room temperature, that means at 25 degrees centigrade, the 1 upon beta hc value is equal to, that means kbt upon hc, because here beta is equal to 1 upon kbt, so it is approximately equal to 200 per centimeter. Okay, this was one of the method how to derive this relation. You can simply use one more method. If you put this beta hcb j into j plus 1 equal to suppose x, and that means j into j plus 1 will be equal to x upon beta hcb. So it can also be written as j square plus j will be equal to x upon beta hcb. So you can also write it as 2j plus 1 dj will be equal to dx upon beta hcb. And then if you want to solve the integral, that means this integral 0 to infinity 2j plus 1, we will simply introduce these substituted values here, j into j plus 1 dj, so it can be simply written as 0 to infinity e raised power, in place of this we have put this equal to x, e raised power minus x and dx upon beta hcb. So this is constant, so it can be taken out of the integral. That means we can simply write beta hcb and integral 0 to infinity e raised power minus x dx. Now if we give the upper limit and the lower limit, it will be equal to simply 1 minus 0, so it will be equal to simply 1 upon beta hcb. So this is the alternative route to solve this integral. Okay. Now one more important point you have to remember here is that the rotational constant B of many molecules is close to 1 per centimeter and often smaller. But there is an exception of hydrogen molecule for which this rotational constant is basically equal to 60.9 per centimeter. So it basically follows that many rotational levels are populated, you can say occupied at room temperature. Because we have taken the condition of temperature equal to 298 Kelvin, so in the next video we will illustrate this with an example. Okay, thank you.